G'day, my name is Neil, my handle is Wally11. I just want to put my disclaimer here. I accept no liabilities for anything I do and say on YouTube. If you follow along or do something that I've given advice on, you're doing so entirely at your own risk. That said, we're going to have a lot of fun. All my projects are fun. I enjoy what I do on this, so hopefully I'm imparting a bit of knowledge. It's all based on my own experience, and I'm not sugarcoating anything. I'm telling it like it is. So I'm not a professional photographer, or I'm not endowed with any special equipment. I have basically what you'll find in most blokes' sheds or garages in terms of the basics. So that's what I operate with. My background, I've recently retrained myself as an electrical engineer, so I'm trying to break into electrical engineering. Haven't done that yet, but I'm looking for a job. That said, I really love it. I really love playing with electronics and playing with electrical gadgets, but I give other advice, and again, it's based on my experience. I got myself out of debt, I had health issues, I had weight issues, all of these things you'll find on my channel. And I did it the way I did it. I let you guys, I shared it, and if I can do it, you can do it. It's basically, you hear it all the time on YouTube, if I can do it, you can do it. And that's true. I've got a company together. I'm manufacturing the NGEM, the night glow electric marker. These things are made from recycled materials. They have recycled plastic, and they have recycled aluminium PCB. So they're a very simple device, and each one of those it takes one plastic bag and one aluminium drink can out of landfill. So because we're targeting materials that otherwise would have gone into landfill, and we're recovering that and making it into these, we're providing local jobs, and we're growing, we're building. So we've just come out of product development. There's been a lot of research in that, and we're moving forwards. So can you support nightglowmanufacturing.com? You can order a pack of those and help save the planet, and provide jobs for people and feed me. That would be good. All right, that said, I want you to like my videos, subscribe to my channel. Again, everything that you do, and if you're following along, it's entirely at your own risk. I accept no liabilities for any of it. Righto, let's get into it. Let's get into today's project. Okay, so if you've been following along in this series, we've been discussing the PWM and the square wave, and I'm going to abandon this series and refer you back to my Blink Like an Arduino series, and it actually achieves the result that's achievable with this chip, with the PIC 12F675. And the reason I'm abandoning this particular series here at part 5, we failed, and we're going to get in and discuss that. And we're going to go back through what we learned by attempting it with our chip. We're going to revisit everything we've learned. So for those of you who are looking to generate a PWM with one of these, there's already a piece of information up there that I put up some months ago called Blink Like an Arduino, where it uses this 12F675 with this particular setup here. And I take you through building this and producing that output in the same manner that I've talked about it here. So I've really gone back over old ground. So what I'll do is I'll go back to part 1, and I'll insert a thing to say, look, this is a failed project, which it is. We failed. We couldn't get there with what we chose. We need to add way more circuitry to our design in order to get there, and I'm not doing that. I'm not prepared to do that at this point. I'm a bit skin on funds and whatnot, so I'm not doing anything else with it. So that said, if you prepare, if you've come through this far, you should by now understand the PWM, and that you can achieve these things if you've got a high frequency processor. You need a really high frequency processor in order to deal with these high frequencies. So it's a problem. It's a problem in communications. We ran up against it at a very low frequency, and I mean we can build a blinking light circuit, you know, like this at 25 hertz. We can do that, and we've proved that. So I'm going to just move on, and at this point I'm going to say this project has failed, and I'm now going to go in and explain why. Hey, welcome back to part 5 of our series on the pulse width modulation, PWM. This series has gotten off track. It's been a bit of a learning experience, and what we were attempting to do was generate a PWM by pulsing high, putting the processor to sleep, pulsing low, putting the processor to sleep, pulsing high, which is the correct way to do things, without any external circuitry in the processor that we chose, which was the PIC 12F675. Now, we went off course, horribly off course, in parts 3 and 4. And through that learning process, I've left it all in, warts and all, so that you can see that it's easy to get sidetracked and confused when you don't have a plan. Now, we did have a plan. We had a great plan, and the problem we ran up against is that after doing further investigation on the abilities of our chip that we chose, our PIC 12F675, this one, right, a little 8-pin IC, nice and cheap, nice and common, easy to get hold of, you know, low power, had everything we thought we needed. And now we find that it doesn't do high frequency in sleep mode because it's got an 18 millisecond timer prescaler. The minimum prescaler for this for the Watchdog Timer is 18 milliseconds, and that's nowhere near fast enough to do high frequency. So our PWM can't handle frequencies over like 20 odd hertz, 25 I think we said was the maximum it could do, and even there it was a 50-50 shot at 25 hertz. So we're kind of caught between a rock and a hard place in terms of the series with this chip, you know, to do the kind of program that we wanted to develop, because the goal was that you feed the program your hertz and your duty cycle, and it would go ahead and give you your PWM, and we were going to do that in such a way that, you know, using assembler, which is quite difficult. It was pretty challenging. It's challenging to achieve that in assembler. In C, it's a lot easier, right? In C, you can do all this stuff just with scripts, and coming up with the scripts to do that in C is way simpler than doing it in assembler. However, I don't think you really understand a chip until you work in assembler. You know, like these things here, they're extremely powerful, and to a great degree, the tools inside the languages of C and, you know, C# and Fortran and all these languages that are out there that people can use, there's all sorts of them. You know, you can go out and you can specialize in doing that language, and you can quickly come up with a solution for that, right? And it'll work, but it might not be the most efficient way for it to work. So what I was attempting to do was to work with assembler so that we work with the basic ones and zeros of a chip, the basic instruction sets. And though they're really powerful. I mean, basic is powerful. Don't think just because it's a basic instruction set that it can't do something. They sent people to the moon with basic instruction sets, what we would consider laughable today. They sent people to the moon with that, and it was all binary punch card stuff. You know, they programmed those things with paper tapes and binary systems. So don't you go thinking for 1 second that you know, basic means not powerful. I grew up in that era, by the way. I grew up with paper tapes, punch. I worked with those. We worked in, when Fortran came out, we thought it was something brilliant. It was one of the 4GL languages, and the thing that we were using was a card reader to program Fortran to do basically spreadsheets. So nowadays, spreadsheeting is like it's second nature to people, and they use spreadsheets for all sorts of things. And it's the same with chips. You use these chips for all sorts of things, and sometimes you use them in the wrong way with the wrong tool. And what we've done by doing or working with this chip in assembler is understand the nature of the chip and what it can and can't do, right? So that's kind of significant. I mean, it is. Now, it can do the job, don't get me wrong, but you need to add circuitry outside the chip. You need a real-time clock. And I guess the way to think about this project with the kind of software we've got in mind is to actually use the real-time clock. Now, an RTC, real-time clock, you know, these are all acronyms that you're going to hit if you start working with microprocessors. RTC is brilliant because it can synchronize multiple things, right? So if you've got a single RTC sending out a clock pulse, and everything can read that pulse that you're using, right? Everything that you're using, every chip you've got can read that single pulse. Well, then everything can be in sync, right? And you can put the same kind of clock in a different device, the same pulse, and it can also transmit its signal out and synchronize, right? Everything can synchronize out to whatever's going on out there, provided the transmission speed is fast enough to get the clock pulse. Does everyone understand that? So if your clock pulse isn't going out there fast enough, your RTC is useless. Now, there are gigahertz things out there. There are, you know, there are things out there that can transmit at ultra high frequency and UHF. And, you know, megahertz is usually fine for what most people are doing. If you're sending a signal to Pluto, you know, a megahertz signal can degrade substantially between Pluto and Earth because of the distance of the transmission. An AM signal will actually sustain a lot better getting from Pluto to Earth. It won't degrade as much as the UHF, right? The AM can be used as a transmitter, a carrier frequency for the UHF frequency. So what they do is they send a low frequency carrying a high frequency. So you can understand all this stuff when you start to work with these. All right. Let's not digress. Let's stay on track. So we've got to make a decision about what to do. Now, I don't have any RTC chips right now. I don't have one. I can get one, but you know, I basically am a bit skint for cash, and I don't want to really go spend any money. So I've got to make a decision about talking about my PWM. And let's recap. Let's recap the PWM. Let's revisit the PWM and understand what we've said. So we've cleared up duty cycle versus period. The period is the time it takes for one cycle of the signal. So there's a high and a low in this particular PWM. Pulse width modulation has a high and a low, right? And the time it takes to go from high to low and then back to high, these lines here, is called the period, right? Now it's also the cycle. So when you talk about active cycle and passive cycle, right? Active and passive cycle is also correct. But the active cycle is more commonly called the duty cycle. And it is a percentage of the total cycle. or period. And that creates a lot of confusion, right? So I got confused about explaining it in part 2 and in part 1, and I'm clearing that up right now. So this is a period. The period is denoted by the frequency. So at 50 hertz, right? 50 hertz means there are 50 periods a second. There are 50 duty cycles a second. So to attain 50 hertz, where you're manually controlling high and low, you need 100 hertz. You need 100 periods, so that you can say, I want it to be active and then passive. Does that make sense? So to output 50 hertz, you actually need something that's processing at 100 hertz. Now our chip at 18 milliseconds, right, sleep periods in the Watchdog Timer period, right, at 18 milliseconds is actually processing at 50 hertz. So to achieve a 50 hertz signal, you need a 99% duty cycle with a 1% spike, right? So you're going to get with a little 1% drop. So you've got to have a really high ratio of active, or a 1% high and a really high ratio of inactive. That'll work, and you'll get your 50 hertz. But you're limited to what your chip can do in terms of controlling the strength of the output, right? The higher up in frequency you go, the more limited you are up to 50 hertz. And 50 hertz is pretty much maximum. That's it. You've got an 18 millisecond, you've got a wake up from sleep thing that happens too, which is in US microseconds. So I think it was 8 microsecond wake up. So it takes 8 processor CPU ticks. Now the CPU is processing way faster. It's processing in megahertz. So you can use an external stimulus to wake your chip up. You don't need to use the Watchdog Timer. So if you need to be talking in megahertz and gigahertz and whatever else, A, you need a chip that's processing in those speeds, and B, you need an external stimulus. So with our circuit diagram that we've created, we can't achieve speeds up above like hertz, and we're talking 20 hertz probably is the maximum speed we can achieve with what we're trying to do. And we proved that with a spreadsheet. So I'm going to swap over, and I'm just going to recap. I'm going to swap cameras. We set up this, which put our chip to sleep, and proved that putting the chip to sleep did not impact the output, right? So we've got our light on all the time, and this chip is being put to sleep now. So this is not consuming any power other than it's working like a switch. It's just accepting a signal in, a high signal of 5 volts, which it's outputting through its pin to that, which it continues to do while it's asleep. So other than powering this LED, it's not doing anything. So it's not consuming any extra power other than what the LED is consuming to get its power. So what we're going to do now is we're going to talk about how we achieve that and what we've done to date. And let's start with the plan. And the plan was this, right? So we developed, or we discussed all the different types of waveforms. We decided this was an analog waveform, most common in analog situations, but it can be digital. It can be produced digitally. This is digital and this is digital, right? So these are all produced with digital. This is digital. In fact, pretty much everything that's on this page is digital. We discussed what is a PWM. We've gone over that. And then what we did was we set up some kind of a plan, and we did that with a flowchart. Now let's go over and see if I can find the flowchart. Just give me a sec, guys. Right, so we did this. Let me go put that down. Oh, I don't want that. Just stay there. So what we did was we put this flowchart together, and then we went through and identified our methods, right? So from this we started to build a piece of software, and we rapidly got confused because our Watchdog Timer, the function of the Watchdog Timer in the research was in the forums. It was only ever referred to in active mode, and it counts down in active mode and shuts the chip down and resets it. And when we started to read this in the forums, and we got deeper and deeper into it, we disappeared down a rabbit hole researching that, and we understand it now. And what it does is when you activate the Watchdog, whether you're in sleep mode or active mode, it starts counting down. And if you don't reset the Watchdog before it expires, it'll reset the chip, which is great if you're in a situation where you're doing space exploration and the chip freezes or the program freezes, which means the chip will be, if it freezes somewhere in execution and you're out in space, well, you can't go out and flick a switch. You want something to reset the chip and start it up again, right? So the WDT is brilliant for that. And we could have saved various projects that went off into space had it been activated. Not understanding how it works is a big minus. So now that we understand that, and we know that every 18 microseconds, we've got to send some sort of a clear command or a sleep command to the Watchdog. Sleep resets the Watchdog, and clear also resets the Watchdog, clear WDT. So those commands must be somewhere in the cycle. Now here we're not doing that, right? We're starting our thing, we're doing our setup, and here we're doing this. But we're sending in our sleep command here, and this happens way faster than 18 milliseconds. This all happens in the blink of an eye, in a moment. So this is happening in microseconds. And if we get down here to sleep, well, then we've reset the active Watchdog. It's now in sleep mode. So now the sleep Watchdog is working, right? So in the active cycle, no, stay in sleep mode. Now, we might need multiple sleeps to get us to the end of active, right? If we've got if we're talking RPM, if we're talking 20 RPM, this is brilliant for that, because we can cycle it in sleep mode until we hit whatever we need for 20 RPM. And then we hit the end of the active cycle, and then we go, okay, then we set the output low, put the thing back to sleep, which we now know does not impact our chip, right? This is still sleeping, this is still active. If we set the output low and then put it back to sleep, it's not going to change from low until we do something else. In which case we keep it cycling around until we hit, yep, okay, has the system been interrupted? No, all right, we go back through the cycle. So we go around this cycle, then we go around this cycle, and we keep going. Now that's cool, and we've identified the methods we need to make that happen. Then we went and identified our properties within the system, and we need our pin, our frequency, and our active duty cycle. We don't need CPU speed, that's a given, right? We know that once we choose a chip, so we don't need to input that. It's just a figure that we use. And most are going to be 1 megahertz, right? The cycle, the period will be mostly 1 megahertz cycle. They have a processing speed of 4 megahertz, which means they've got 4 highs, 4 lows, 8 bits. Means you simply divide by 4. Does that make sense? You've got 4 highs and 4 lows in a cycle. So that gives us a total of 8. So, you simply divide 4 megahertz by 4. So you're processing at 1 megahertz. That's cool. All right, let's stay with this. Let's keep on track. So we know our properties and we know our methods based on all of this planning. And then what we did was we went down a rabbit hole. But we went backwards out of the rabbit hole into our data sheet. Oh goodness, I didn't save the data sheet in here. I'm not going to worry about that. But we went to the data sheet, and in the data sheet on page 66 of the 12F675 data sheet, we found the WDT period information, which allowed us to put this spreadsheet together. Oops. So in this spreadsheet, we went ahead and we plugged in our 18 millisecond cycle for our Watchdog Timer. This is Watchdog, WDT stands for Watchdog Timer. I keep losing my... Oh, I'm opening up crap I don't want to open up. Okay. So we worked out what the prescaler meant from the data sheet. We didn't go to forums. We ignored them because it sent us down a 3-week rabbit hole, which we didn't come back from. So we're still out there in the rabbit hole, and forums are great things, but they can confuse the crap out of you if you don't have this information in front of you. So we now know that it's that our Watchdog Timer, our WDT Watchdog Timer, has two functions. It's got an active function and it's got a sleep function, right? And in sleep, what it does is it wakes the chip up. And that's the bit we're interested in. When it wakes the chip up, we can set the prescaler in active mode to 128. So when we're in active mode, we can actually, you know, set the Watchdog cycle to its longest 2.3 seconds. Right? So we don't have to worry about resetting it for every 2.3 seconds. It'll continue to run. So that's something we should do straight up. We should somewhere in our setup be setting the Watchdog setting to its default of 128, its maximum. So when we're using the chip, we've got 2.3 seconds before we've got to issue a sleep command. Right? Now, if the chip freezes and 2.3 seconds expires, it's gonna hit Watchdog timeout and reset. So that's interesting. That's an interesting concept. So that should be built into our software. We need to build that in, and so we need to change our flowchart. So one of the first things we're going to do is go back to our flowchart, and we're going to revise it based on what we now know. Now, that said, we can't build a PWM subroutine based on this, right? Because we're making it chip specific. So we can't build it as a generic approach when we're working with one chip, because things are going to change when you go out and use, say, a 16-bit chip or a 32-bit chip. You're going to get different clock cycles, right? So this number's going to change, and these numbers are going to change, and all this is all going to change. I'm just going to change this back to 25 Hertz, which was what we were going to work on. Every time I do that, I lose my... Right. I'm just going to move this across so people can... We put this table together so we could understand frequency and what it means in milliseconds, in period. We created the same formula over here. So at 25 Hertz, our period is 40 milliseconds. And if we want a 50-50 duty cycle, right, then we can do it, because this is close enough for us. A 2 millisecond gap is fine. So the Watchdog timer is fine to create a 50-50 duty cycle, a 50% duty cycle of 25 Hertz. We can use our chip. We don't need any external hardware, and we're fine. we're cool. This is useful information. This is extremely useful information because 25 hertz is 1,500 RPM, right? 50 hertz is 3,000, so half of it is going to be 1,500. And you can convert from hertz into RPM by dividing by 60, multiplying by 60. Let's get it right. Multiply by 60. From hertz to RPM is you multiply by 60. So 50 hertz times 60 is 3,000. If you're going the other way, you divide by 60 because there's 60 seconds in a minute. So you're just converting it to revolutions per minute by using 60 seconds, okay? Whichever way you're going. Don't get it the wrong way because you'll end up going way too slow or way too fast. So make sure you go in the right direction. Okay, so here at 20 milliseconds, we can do a 25 hertz signal. No, not a worry. We can do that with a 50% duty cycle. Yep. And we can output 25 hertz at 50%. At some point, we're going to sweep this value a little bit. Right, well at 60% we can't do it. But what about at 52%? Yep, we can do 52. What about 53? You can do 53. What about 55? Okay, I'd say 55 is all she can handle. So we can do 25 hertz at a 55%. You're not going to notice it anyway, right? It's going to be the same as I don't know where it becomes 0. I mean, %, 46, 48, 49. Okay, so basically the WDT is a 49% active duty cycle. Because you can see our remainder here hits 2 milliseconds for both active and passive. So at 49%, we're fairly accurate with 2 microsecond inaccuracy, you know, which is against 49, 2 over 49, it's about 2%. Pretty close, give or take. About 2% accuracy, plus minus 2%. You'd be pretty happy with that. I mean, you'd be pretty happy with that if you were trying to achieve something, because you've got all sorts of external influences on your signal too. So you've got, you know, you've got static and you've got all sorts of things that we're not filtering out in our circuit. So let's go back and visit the circuit now. Let's go back to that. We want to. Right, so I'm going to stop talking about that right now, and I'm going to refer you guys to my Blink Like an Arduino project. But we're going to move forwards and talk about that project because it actually achieves this PWM, right? So it does this, and it does it at a very, very low frequency. So it blinks the light and puts it to sleep. Turns the light off, puts the chip to sleep, and what we've discovered is that when the chip's asleep, it doesn't affect the output pins, right? So it's still, if it's made the bridge in the chip, if it's made the connection to the pin from VCC via its transistors to an output, it doesn't change the state of those transistors in sleep mode. So whatever's being output still gets output through power, right? Now, if you're cycling something based on a processor, whatever state that output's in when the chip goes to sleep, that's where it's going to sit. It's not going to keep cycling, right? It's going to sit at wherever it was at whatever point in time you put that chip to sleep. So if it's a high, it's going to stay high, and if it's a low, it's going to stay low, right? So just be aware of that. And we've proved that. We've actually built software in this series to prove that. So if you've got nothing else, we've understood the PWM, we've understood the Watchdog Timer, and that's enough for this. I think that's a good point to leave this series, abandon what we were trying to achieve with the programming, and move on to a different project which involves more circuitry and more complex discussion. So let's just go on, and I'm going to refer you now into my Blink Like an Arduino project. I want to talk about this circuit. What we did was we built this circuit in Blink Like an Arduino, and what I've done is I've borrowed it and reproduced it here for our PWM test circuit. And it's the exact same circuit that we used in Blink Like an Arduino. This chip holder was all I had available to me, so that's what I used. It doesn't need to be this big, but you only need 8 pins, so we're only using this socket up this end. So all the wires run up to this end, and then they run into the pins as per this wiring diagram. So once again, everything I'm doing here is open source. The general the GNU. The general something users license, use at your own risk and no warranties, right? So if you're following this, great. If you're building this as you go, great, but you do everything at your own risk. Right, the 200 ohm resistor in here, the bigger you make the resistor, the duller your LED is going to glow, but the less power it's going to consume. So I've had a 1K resistor in there. I still get an LED that glows. I'm not sure what's on this. There's probably a 1K resistor in there, not a 200 ohm, because they're pretty common, 1K resistors, and I've got heaps of them. But you can use whatever number you want, provided you can see that this is glowing. So, even a 10K resistor, this will still glow, but it'll be a very weak glow. It'll just glow. Pin 1's the arrow. So we've built this, we've done it, we're moving on. We've got this, we've decided we can do 25 Hertz with a 49% duty cycle. So basically, I'm happy at 25 Hertz. It's the Watchdog Timer in default mode, 0, which is the default, is going to give us a 49% duty cycle with a 2 millisecond error, right? In both, and the error is going to be consistent. It's going to be consistent for both active and passive. About this bit of code, this was a bit of quick and nasty code that we put together just to make sure that the GPIO output is unchanged when the processor enters the sleep mode, right? So this piece of code here is what we use to prove that. So it's a neat piece of code. It follows our doctrine of object-oriented design. Hang on a sec. I'm looking for our flowchart. In test, this code is in here, right? This test GPIO and sleep, this ASM file. I'm going to release that in the repository in Git, so I'll put a link to that. And somewhere in here, I've got my very simplified little flowchart. Oh, goodness me, I've lost it. I had test 1 and test 2. I'll find that flowchart and put it into the same repository. Okay, so I lost the flowchart, but good news, I had it on video, so I just grabbed it off the video. So I'll put this flowchart up in the documents as well. So those will be available to you. You'll have the code and the flowchart and the design and the circuit diagrams. So that will all be put for your convenience into the Git repository, along with the code that we started to develop. I'm going to release that. It's not complete, but you might like to have a twink and play with it and see where you end up with it. Okay, so we're going to stop this project. We're going to call it a fail, but in failing we've accomplished a couple of things. We understand the pulse width modulation. We understand what it is, right? We've talked about the various aspects of it, of its properties, and how you have an active and a passive cycle. The active cycle is also called the duty cycle, and the full cycle is called the period. So we know that. We know that when you turn a pin or set a pin active or high, it's not impacted by putting the chip to sleep on the 12F675, and I suspect for pretty much every microchip chip that's out there, if you put the chip to sleep, it maintains its output at whatever state the output was in when it went to sleep. So we've established that, which is also very, very good for us. Finally, we've established that just using the circuitry within your chip and the Watchdog Timer, you can produce PWMs, such as was done with my Blink Like an Arduino piece of code. And now that we understand the Watchdog Timer and what it means using that spreadsheet, and by the way, I am releasing the spreadsheet as well, so that's also going up into the repository. Excuse me, a bit of lunch. Hang on a sec. Eee. Nice. It's a cup of tea. It's after lunch. I don't know. I've been feeling off, and I'm not tracking too well in terms of health. But you know, you got to eat and you got to drink. You've got to stay hydrated. It's really hot today, and it's threatening to storm, but it's not quite there yet today. It was the other couple of days. It's been storming in the afternoon. It's about to get going again. Alright, so we're going to close off this project. We're going to say we failed. We didn't produce the piece of software we wanted. I am going to release all of the documents that we've got up to this point. And look, I recommend that if you want to get into this sort of stuff, you start looking into real-time clocks and how you can use the real-time clock to give you an accurate PWM. Because this is all about communication, right? Once you understand this stuff, the next step is to move into real communication. And so I think that's the next step for this, is to stop this project and start a brand new project where we're going to use these, right? And we're going to build ourselves a transceiver, one of these things. Now, why build one, you ask? Well, it's easy, so we can understand it. You can buy these for next to nothing. They're very, very cheap, and they can handle all sorts of frequencies, you know, very easily. In Arduino, you know, you just buy the bits in a kit and away you go. You write a program and it just works, but you don't really understand this. You don't really understand what did it take to put this together, right? Right, this chip, very common. I think what we're going to do is we're going to talk about researching the RTCs. I know that there's again plenty of rabbit warrens to disappear down into, because Communications is one of the most confusing things that you will ever research, and I mean confusing. There's literally thousands and thousands of things out there that will lead you astray. So you've got to follow the principles that we set up here in object-oriented design. Draw out your flowchart. Make sure that you've got a clear picture of your start, your middle, and your end. Make sure that you're in the right environment, that your chip, that your hardware that you're specifying, it all plays well and talks to each other, right? If it's not compatible, you got problems, and you got to build circuitry to solve those problems. You don't want to be doing that. You want everything to work and play nice. So you've got to research, look at what other people have done by all means, look at it, but don't be drawn off your pathway. If something's going on, like we got told the Watchdog Timer doesn't do what you thought it did, well, you know that's wrong, and it didn't reconcile, and so you set up a bunch of research around it. And okay, I disappeared down a rabbit hole for a couple of weeks here, but I'll tell you what, my understanding of the Watchdog Timer now is pretty spiffy. You know, I can use that thing, and I know how to use it. Had I not disappeared down the rabbit hole and found the solution for myself, I'd still be in a mess of forums with blokes arguing with each other, and, you know, it just goes into ridiculous. All right, all that said, I want you to make good decisions and do good things. I want you to like this video if you really enjoyed it. If you didn't enjoy it, like it anyway. Send someone else on a mission of horror. If you subscribe to my channel, you'll get notifications and things if you click the post notifications. And just make sure that you support my company, nightglowmanufacturing.com, because these NGEMs, right, there's a lot of engineering that's gone into these, and every time one of them is bought, that's one plastic bag and one aluminium drink can that would otherwise have gone into landfill, right? So I'm going to be coming up with different products in terms of the NGEM. This is our flagship product. It's a night glow electric marker. It runs off one of these, and these have all been recycled, right? All the ones I've got in those, I've actually got them out of old computer boards, so these would have been in landfill, and the components for this would have been in landfill. So I've got these out of landfill, and so it's keeping that out of landfill, that out of landfill. All this stuff would have otherwise gone into landfill. See, my company is an eco manufacturer, and we are looking to find ways that we can save the planet. And so nightglowmanufacturing.com is all about that. There's a Facebook page if ever you want to look us up on Facebook. We put a lot of stuff on Facebook. And I don't know how to use everything up there yet, but I'm getting there. I should know how to use it because I've been exposed to it for so long, but I seriously don't use it as the way I should. I don't have Instagram, for example. I don't do that. I'm not intending to do that either. You know, that's not where I'm at. I'm not looking for fame and fortune and stuff like that through this media. I'm looking to save the planet through this media, right? That's what I'm looking for. And I can employ some people and feed my family at the same time if you guys will buy the product. So by all means, go out and buy the product at nightglowmanufacturing.com. Right? Nightglow. Cup of tea time. Definitely cup of tea time. Holy mackerel. It's a really hot day here. It's muggy, it's hot, it's oppressive. We don't run air conditioning here. We have fans and a window, which is currently closed for some reason. Oh, I know why that was done. We don't smoke here either. None of us smoke, so when someone goes out there and smokes, it drifts up through the window. So we close the window. I don't know. All right, so I want you to make good decisions, do good things, like the video, subscribe to the channel, turn on notifications, ring the bell, and look, just keep on at it. Just keep plugging away at whatever your project is. If you're still looking for info, you know, just keep on swinging at it, and you'll get there. You'll get there. If it's a good and worthy cause, you need to get there. And if it's something that's something else, well then, you know, forget it and go on with something that's good and worthy. You know, build things that improve your life. Build things that improve other people's lives. And how can you go wrong with that? And do it sustainably. Do it in a way that you're saving the planet. And that's what we're doing. We're saving the planet. We're recovering these chips out of dead circuit boards. We're recovering batteries out of dead circuit boards, and we're charging them up and reusing them. And they'll accept the charge. It's dangerous practice, and we have a specific way of doing that. But we can charge them and recycle them back through our systems. And we will recycle this when it's finished, when it's dead. You can send it back to us, and we will completely recycle it. 100% of that can be recycled. So, it's a big opportunity to change the way we all interact with our planet. Okay, I'll see you at the next video.